Today, we tackle a problem involving bus routes. Imagine a circular path with several bus stops. Your task is to find the most efficient way to travel between any two given stops. Sounds simple, but the circular nature adds a twist. Let's dive in. We're given an array called distance, where each element represents the distance between consecutive bus stops. This route is circular. We also get a start stop and a destination stop. Our goal is to return the shortest distance between these two stops, considering both clockwise and counterclockwise paths. For example, if stops are 0, 1, 2, 3, and the distances are 1, 2, 3, 4 from stop 0 to 1, the direct path is 1. A straightforward but inefficient approach would be to calculate the distance for every possible path. You could iterate from the start to the destination clockwise, summing distances. Then, you repeat this for the counterclockwise direction. This involves nested loops or multiple passes over the array for each path calculation. While it would eventually find the minimum, it's highly redundant. Each path calculation involves resumming segments of the array that might have already been processed for another path. This leads to a time complexity of n squared in the worst case, with big O of 1 constant time space. The key insight here is that for any two stops on a circular route, there are only two paths, clockwise and counterclockwise. The sum of these two paths always equals the total distance of the entire circular route. So, if we calculate the total distance once, and then calculate the distance for one direction, say, clockwise, we can find the counterclockwise distance by simply subtracting the clockwise distance from the total. We start by calculating the total distance of the entire circular route by summing all elements in the distance array. Then, we iterate from the stop towards the destination stop in the clockwise direction, accumulating the clockwise distance. To handle the circularity, we use the modulo operator to wrap around the array indices. Finally, the counterclockwise distance is simply total distance minus clockwise distance. We then return the minimum of these two distances. Let's trace this with an example. Distances 1, 2, 3, 4 from start 0 to destination 1. First, calculate the total distance. 1 plus 2 plus 3 plus 4 equals 10. Next, we calculate the clockwise distance from start 0 to destination 1. We start at index 0. The distance from stop 0 to stop 1 is distance at index 0, which is 1. Our loop condition checks if we've reached the destination. Since we're at stop 1 and our destination is stop 1, the loop terminates. So, clockwise distance is 1. Now calculate counterclockwise distance. This is total distance minus clockwise distance, so 10 minus 1, which equals 9. Finally, we compare clockwise distance, 1, and counterclockwise distance, 9, and return the minimum. The shortest distance between stop 0 and stop 1 is 1. This is correct because the direct path from stop 0 to stop 1 has a distance of 1, which is clearly shorter than traveling all the way around. You'll spot this pattern when dealing with circular arrays or routes where there are exactly two opposing paths between any 2 points. It's a strong indicator that calculating one path and the total sum can give you the other path, avoiding redundant traversals. The time complexity is big O of n because we iterate through the array twice at most, once for the total sum and once for the clockwise distance. The space complexity is big O of 1 constant time as we only use a few variables. This circular array pattern is quite common. Try the next problem involving circular buffers to reinforce this idea. Don't forget to like and subscribe for more DSA insights.